So now that we have handled all the calculus for time-inhomogeneous Poisson processes, we have substantially more freedom in specifying models for real-world processes. Indeed, as you will see, the modeling process now not only consists of specifying a stochastic generating mechanism, but also postulating a functional form for the intensity function in such a way so as to mimic empirical features of data that we observe in nature. So for today's lecture, we'll look at conducting likelihood inference at the hand of interarrival times for time-inhomogeneous Poisson processes, and then we'll look at a practical application in order to demonstrate the machinery. So let's jump in. Cool, so let's look at constructing the likelihood for a time-inhomogeneous Poisson process model. Okay, now recall that for a homogeneous Poisson process with rate parameter lambda under, say, fixed window mode, where we observe n star interarrivals to give us a dataset cal d, which the interarrivals are just given by t1, t2, all the way up to tn star, it follows that the density approximation to the likelihood function is simply the product of the density function of the interarrival times, which under that model specification is just the exponential distribution post-multiplied by the probability of observing 0 events in the remaining time interval after the last observation in the time window over which we work. Okay, and when we simplify that expression, we simply end up with a likelihood function which is lambda to the power n star times e to the minus lambda b, where b is the endpoint of the observation window. Okay, now we can then go and we can maximize this quantity with respect to the single parameter of the process, lambda, to arrive at a maximum likelihood estimate, lambda hat. Okay, and in this case, we saw that that expression is analytically tractable, so we could write down an expression for what lambda hat should look like if I give you a dataset. Now, in the time-inhomogeneous case, we have the added complication that the intensity function varies with respect to time. So the true underlying intensity function may, for example, take on a form, say lambda t equals 2 plus 3t. But in the context of modeling, okay, from our perspective, the intensity function is unknown, right? So we have to postulate a parametric function for the intensity function, which hopefully reflects the nature of the true underlying intensity function. Furthermore, for whatever parametric function we postulate, we need to ensure that it does not produce nonsensical values for the intensity along the time domain over which we observe the process. So i.e., it probably needs to be appropriately constrained. Let's consider, for example, a expression for the intensity function, or a parametric expression for the intensity function, lambda t equals beta 1 plus beta 2t for t greater than naught, with the parameters beta 1 and beta 2 greater than or equal to naught, respectively. This constitutes a linear parametric intensity function where the parameter constraints ensure positivity of the intensity function. So remember, it wouldn't make sense for the intensity function to be negative. Okay, it has to be positive. Okay, so now we have a parametric model. Now, selecting an optimal, in whatever sense, set of parameters suggests that the estimation problem, so i.e. estimating the values for beta 1 and beta 2 if I give you a data set, will become a constrained optimization problem. However, careful specification of the intensity function and or an appropriate parameterization can actually be used to enforce positivity constraints, yielding an unconstrained optimization problem. So for the present example, for example, the positivity of the intensity function under such a linear specification can be enforced by a simple reparameterization, where we set lambda t equals e to the row 1 plus e to the row 2 times t. And this is for t greater than naught, where row 1 and row 2 can now take on any values in the real line, respectively. Okay, and we refer to these parameters as working parameters for our optimization problem, from which we can then, of course, recover beta 1 and beta 2 in the obvious way. Okay. Now, it should be obvious at this stage that depending on the particular problem you're working on, an appropriate intensity function might be something much more complicated than what I've presented here. Indeed, I've just presented possibly the simplest case, simple linear intensity function. Indeed, I'll include some references to papers which deal with quite complicated specifications on screen that you can check out. But the choice of intensity function is often informed by a mix of the particulars of the underlying problem, as well as some skill or experience on the part of a statistician. In any case, it will invariably require some skill both numerically and statistically to identify a good model anyway. Okay, so let's just park that for a second. That's that for specifying the intensity function for now. Next, we need to deal with the likelihood under a given model specification. Okay, so for this, we make use of the following theorem. Theorem goes as follows. Let nt for t greater than or equal to naught denote a time-inhomogeneous Poisson process with intensity function lambda t, mean value function mt, with arrival times, capital SI for I running from 1, 2, 3, etc., and inter-arrival times, capital TI for I running from 1, 2, 3, etc. Then the inter-arrival times are independent, and the conditional PDF of the ith inter-arrival time, given that the I minus 1th event occurred at time SI minus 1, can then be written as, and we'll denote the density as, G for capital TI given SI minus 1, evaluated at T, is just the intensity function evaluated at SI minus 1 plus T times the exponent of minus MSI minus 1 plus T minus MSI minus 1. Okay, so the mean value function evaluated over the interval running from SI minus 1 to T. Okay, and this should hold for all I running from 1, 2, 3, all the way up to N. Okay, and where we use the convention that S naught is equal to naught, okay, since the process is you start observing the process from time naught, and the first arrival time will be given after that point in time. Okay, so that's our theorem. This is the conditional density for the ith inter-arrival time, which we will again make use of in constructing the likelihood. Now, the proof of this statement, fortunately, is not too complicated. First, we note that the independence follows from the fact that the increments of the process are independent. Okay, so remember this is a conditional density, so conditional on the I minus 1th event at time SI minus 1. Okay, so we know that event has just occurred at that point in time. We know the history of the process up to that point in time. What is the distribution of the next inter-arrival? Well, the increment over that, whatever that time window may be, is independent Poisson. Okay, we know that, so it follows that the next inter-arrival will be independent. Now, for actually finding what the PDF is, we also note the following. We note that the events that capital TI is greater than some point T, okay, given that SI minus 1 is equal to SI minus 1. Okay, so I give you that value. T is some time elapsed after that point in time. The events that capital TI is greater than whatever that point in time is that you fix T coincides. So it happens if and only if the increment of the process up to just before that time, so the increment over SI minus 1 to SI minus 1 plus T is 0. Okay, that is the only way in which that can go. In consequence, since the increment, right, so that NSI minus 1 plus T minus NSI minus 1 is just Poisson distributed with the mean given by the mean value function evaluated at the endpoints of that interval, so MSI minus 1 plus T minus MSI minus 1, we have that the probability associated with the event that Ti is greater than T given Si minus 1 is just the probability that the increment is equal to naught. Okay, and from the Poisson distribution, so our calculus result that we had previously for time-inhomogeneous Poisson processes, we can evaluate that expression exactly. So that just gives us that exponent to the power to the minus MSI minus 1 plus T minus MSI minus 1. Okay, and from which we can actually derive the density by simply taking an appropriate derivative, right, of 1 minus that probability. Okay, and that gives us the result. Okay, excellent. Now, given a model intensity function, lambda t, which is parameterized now by some vector of parameters, which we will denote boldface beta, we construct the likelihood in terms of this conditional density as follows. So first, let's consider fixed count mode, where we observe exactly n interarrivals to give us a data set cal d, which is just t1, t2, all the way up to tn, from which it then follows that the density approximation to the likelihood function is simply the product of those conditional densities, all evaluated at the appropriate arrival times. So the product of I running from 1 to n of lambda si minus 1 plus ti, okay, and you evaluate the intensity function at the particular value of the parameter vector, times e to the minus msi minus 1 plus ti, where the mean value function is also evaluated at the appropriate parameter value, set of parameter values, minus msi minus 1. Okay, and now what's going to happen as we take that product in, we see we end up with a product of intensity functions just evaluated at the ith arrival times, okay, post multiplied by a simple exponential e to the minus msn, so the last arrival time, minus ms naught, where s naught is the start of the observation window. Okay, and we evaluate again the mean value function at the appropriate set of parameters. Okay, now how do we arrive at this expression? Well, if you take that product in, you will see that the msi minus 1s, those terms start telescoping, so you end up evaluating the mean value function simply over the observation window, or at the endpoints of the observation window, which is s naught and sn, so the time at which you observe the last arrival, so the nth arrival. Okay. Now, for purposes of finding the maximum likelihood estimate, well, that is just the point, boldface beta hat, in the p-dimensional now parameter space, because remember our intensity function can have multiple parameters. Let's just say for argument's sake there are p of those. Well, it's just that point in the p-dimensional parameter space which maximizes this quantity, the likelihood function. So I give you a data set, you have a parametric model, you can construct the likelihood function in terms of that parametric model. Your job is then to maximize the likelihood function with respect to that parameter vector, find the point in the p-dimensional parameter space which maximizes that function, and that gives you the maximum likelihood estimate for the parameters of your model. Cool. And now obviously we again have another observation mode, which is fixed window mode, where in this case we observe n star interarrivals to give us a data set t1, t2, all the way up to tn star, from which it again follows that the likelihood function is now again just the product of the conditional densities, but now again post multiplied by the probability that we observe 0 events in the remaining time after the last event has been observed, okay, to account for the fact that we observe the process over a fixed window. And again, a similar thing happens. You now see telescoping twice, okay, so we end up with an expression where we have an exponential to the minus mb minus ms naught. So again, evaluate the mean value function simply over the endpoints, or at the endpoints of the observation window. Okay, and that gives you your likelihood function. And yeah, as usual, what we can do is more convenient to work with the log likelihood function, so we simply take the log of that expression, and as you can see, well, turns out it's not too complicated to construct the likelihood function under either observation mode. It's just a question of finding the appropriate parameter or set of parameters. So, in closing, for purposes of conducting likelihood inference, we need to look at the empirical features of the data, then specify an appropriate parametric intensity function, also making sure that any constraints are satisfied. Then, depending on how the data are observed, so i.e. is it fixed count or fixed window mode, we construct a likelihood function in terms of the observations and the intensity function and the mean value function under the chosen parameterization. Okay, we will then have a likelihood function, which is a function of a parameter set. We can then maximize the likelihood analytically, Okay, so with respect to each of the parameters, we can maybe find an expression that we can write down, or where it is analytically intractable, we can just maximize that function numerically. Okay, and that gives us our parameter estimates and subsequently model statistics under which we can conduct inference and probe for answers to any statistical questions we have about the true underlying data generating process. Cool, so now let's look at an example application where we'll go through the process of specifying a parametric intensity function, deriving constituent parts of the likelihood function, and then we fit the model to some data. Okay, so consider again the data from the 2020 Cape Peninsula Marathon. Recall that for this data, we observed the process over a window running from 0 to 400 minutes, and then recorded, in minutes, the arrival times at the finish line of runners. We then broke up the observation window into little sub-intervals or bins of width 10 minutes, and then we calculated the frequencies of runners arriving in those bins. Okay, and what we observed was that, well, at first, the frequencies were 0 for a while, and then after that, it started to increase quite sharply. It then peaked and then subsided again, almost in exponential fashion. Okay, so clear temporal dynamics in the observed data. So, for our purposes, we'll now attempt to model this data using a time-inhomogeneous Poisson process. Cool. Now first, let's pre-process the data a bit. Okay, so let A1, A2, A3, etc. denote the raw arrival times in minutes of the runners. Okay, then first what we'll do is we'll discard any observations after the 360-minute mark. Okay, why do we do this? Well, this coincides with the 6-hour cutoff point of the actual marathon. Okay, so because we're modeling a marathon finish times, we'll just cut off those observations, throw them away. Okay. Second, what we'll do is we'll shift the data so that the arrivals correspond to the time elapsed after the 120 minutes mark. Okay, so why do we do this? Well, this is a plausible lower limit for a marathon time, so around 2 hours. Okay, why do we do this? Well, remember that for the first 2 hours, we don't actually expect to see anything. So there's no point in trying to model that. The intensity at that point will have to be 0. Okay. So what we do is we in fact now shift our data, okay, so that under our model process, the actual arrivals, which we now denote SI, is just the AIs minus 120. So we subtract 120 minutes from the observations, and that means that the ith arrival time is now the time elapsed after the 120 minute point for the ith arrival, and the origin of the time domain, so 0, now corresponds actually to the 2-hour mark of the original marathon. Okay, so we just shift the data for pragmatic reasons. Okay, cool. So what that means is we now model the process by defining a parametric intensity function in t on the window running from 0 to 240. Okay, so this is in shifted time. Okay, and what we need to now do is specify an appropriate intensity function. Okay, and how we're going to specify this parametric intensity function is again with reference to our little frequency plot. So what did we see? Okay, so even if we shift the data, we specify our window. Within that window, what do we see? We see a quick exponential climb, a slower exponential climb, and then again a little exponential decrease. Okay, so what we need to do is specify a function which sort of mimics that pattern. Okay, so let's then suppose that we model the intensity function as a set of grafted exponential linear functions. Okay, where I've defined the intensity function, lambda t, which is now a function of a parameter vector, boldface beta, as piecewise defined in terms of simple linear exponentials, where the first exponential is e to the beta 1 plus beta 2 times t minus 120. And that's for the time for t running from 0 to 120 minutes. So remember, this t is now with reference to the 2-hour mark. So the origin corresponds to the 2-hour mark in the original marathon. The second simple exponential is e to the beta 1 plus b beta 3. So we've got a new parameter there, beta 3, times t minus 120, and this will be for t running from 120 to 170 minutes. And then finally, e to the beta 1 plus beta 3 times t minus 120 plus beta 4 times t minus 170. And this will be for t running from 170 to 240. Okay, so we've got a piecewise defined intensity function, and it will have 4 parameters. So our model will have 4 parameters: beta 1, beta 2, beta 3, beta 4. Okay. Again, why did we specify this function in this way? We sort of aim to mimic the dynamics that we see in the data. Okay. Now note here that grafted means that it's a set of piecewise defined functions which exhibit some semblance of continuity, in that the function is not discontinuous at the boundaries of the subintervals over which we define it piecewise. Okay. So our function will, at the value that it attains at the end of a particular subinterval, it will continue on from that value forward. So there are no discontinuous or explicitly discontinuous breaks in our intensity function. Okay. Yeah, and I guess just another comment to make is, well, the choice of breakpoints here for the subintervals is somewhat arbitrary. And in this case, I specified it by way of inspection and having some understanding of how a marathon works and how to pick those points in time. There are problems in statistics where you can make that a parameter of the model. That's called a change point analysis, which comes with its own complications. But for simplicity's sake here, we'll just assume that my hunch is correct about picking those breakpoints, and we specified in terms of these fixed arbitrary breakpoints. Okay, cool. So we have this parametric intensity function. I claim that it will sort of mimic what we see in the data. If you trust me, we can continue from there. Right, so we've got an intensity function. What else do we need to construct the likelihood? Okay, we need the mean value function. Okay, and moreover, remember, depending on which observation mode you're working in, you might have different specifications of the likelihood function. In this case, we're in fixed window mode, okay, because we have actual fixed start and end points over which we start and stop observing the process. And thus we need to evaluate the mean value function based on this parametric intensity function at the start and end points of the observation window, which in this case is 0 and 240. And indeed, if you look at this intensity function as I specified it here, we can calculate that actual definite integral because all of the integrals are actually analytically tractable, and you can do it as a little exercise and make sure that those are the appropriate expressions. Cool, so we've got our intensity function parameterized. We've got our mean value function in terms of that specified intensity function. We've pre-processed the data somewhat. Now we can get to conducting the likelihood inference. So, in order to fit the model, we find the maximum likelihood estimate, boldface beta hat, by numerical maximization of the log likelihood. Okay, where our log likelihood is evaluated in terms of around 2,344 observations, and the constituent parts which we have now just derived, the intensity function and the mean value function. Okay, and then, yeah, we note that for this specification, the resulting optimization problem fortunately turned out to be an unconstrained optimization problem. Okay, so what does that mean? We didn't have to apply any constraints during optimization to the parameters of our model, because if we look at our model, we will see that, well, there aren't really any values for the parameters that we've set up, which will produce nonsensical values for the intensity function. Now, there are those cases for which the mean value function, if we evaluate it in the way that we did, will not make sense if we use the expressions we had there. But in any case, our numerical procedure will probably be clever enough that when you start dividing by, say, for example, 0, so when you say, let's say, all of the parameters are set to 0, then our expression for the mean value function as we derived it, they won't make sense. But in any case, that integral won't be the integral. It would have been if those parameters were 0. Nevertheless, if we use the wrong expression, we plug in the zeros there, our numerical procedure will probably be clever enough to deal with that. It'll be stepping discretely, and when it steps on that, it evaluates an infinite, and it'll step away from that in any case. Okay, so we're not really expecting issues. But in any case, this likelihood function, we now have the data, we have the model specification. It's now just a question of optimizing that quantity. Okay, yeah, I'm sure you will be able to see that from the parametric specification that I gave you. That will be something very difficult to do by hand or analytically. Okay, so we need to resort to standard numerical optimization procedures, such as, for example, NLM in R. Okay, and indeed, when we do that, we find the following parameter estimates for our marathon data. We estimate beta 1 as 2.9424, so this is rounded to 4 decimal spaces, beta 2 as 0.0315, beta 3 as 0.0042, and finally beta 4 as minus 0.0331. Okay, cool. So we actually have now values for the parameters of a model, and now I can start asking you cool questions based on this model, right? Because remember, now we have some values for the parameters, and now we can calculate statistics and probabilities under this specific set of parameters and the model specification which we had. Okay, now just as a sort of final note, just as a quick sanity check on, do these parameter values make sense? Well, what we can do is we can, for example, calculate the predicted frequencies under this model for the bins that we had earlier, and then compare them to the observed frequencies. And then, yeah, indeed, you will see the shape of the intensity function, or at least the shape that we tried to mimic. And we will see that, okay, we're not that far off the observed values. It's by no means a perfect model, but certainly a good starting point. Cool, so that's that for now. We can follow up the analysis in detail in an R session. Okay. As an exercise, see if you can come up with a better parametric intensity function for the peninsular marathon data. But before I sign off, I'd like to make some comments on the quality of our model. As I've mentioned before, this is a good starting point, but there are still some important features which we haven't explicitly modeled here. Chief amongst these is the so-called clustering effect, what one would observe in marathon finish times. Okay, so that is, at particular points in time, one actually expects to observe clusters of runners finish before that time, and in consequence, see an increase in the frequencies of arrivals just before that time, followed by an abrupt decrease just after. This follows since runners will often have target times which they are aiming for, and indeed there are both qualifying times for longer events such as the Comrades or Two Oceans ultramarathon, which people might aim for, as well as some milestone target times, for example 4 hours, so completing a marathon just in 4 hours, 3 hours 40 minutes, or 3.5 hours, which corresponds roughly to a pace of around 5 minutes per K. And then finally 3 hours for a so-called silver time. Okay, and in fact, most marathons actually have so-called buses, where a quote-unquote bus driver will pace runners in such a way so as to finish within a particular target time. Okay, as such, we see these clusters in our observations, and thus care needs to be taken in order to either explicitly model or control for such effects where it is not explicitly modeled. In any case, this will require that we improve our modeling skills first before we tackle such problems, but do be aware of the effects. They are there. So I hope you found that interesting. I'll leave up some problems, and then I'll see you in the next one. Cheers.